Hi again, welcome back to this MOOC on sustainable mobility. In the previous video lecture, we discussed pollutant formation in the engine and the factors that affect them. In this part of the lecture, we will concentrate on reducing the pollutants. Now, in order to reduce the pollutants, there are two options. First, reduce where the pollutants are formed, that is to say, reduction at the source or at the engine. To do this, we could work on engine design, geometry, dimensions, etc., or add specific technologies to the engine. Or we could include alternative combustion as we discussed in the previous video. We could also work on how to use the engine at different conditions known as calibration, and also how we control the engine in different circumstances. The second option is we let the pollutants being formed in the engine and we treat them later with special systems known as after-treatment systems. In general, the pollutants are reduced with a combination of these two options together. In this video, we will discuss the first option. We will take examples of some of the main technologies which are part of engine design today. Everything else, combustion, calibration, and control are out of the scope of this introductory classwork. Before we go further into pollutant reduction, let's do a quick recap. So, from our discussion in previous video, we know that pollutants are either product of incomplete combustion or they are byproduct of combustion. Also, we know that the gas composition and temperature together guide the combustion process as seen on the right of the slide. We have also seen that CO is produced in rich combustion, HC is produced due to incomplete combustion. Sometimes, especially in gasoline engines, fuel is trapped in engine corners where flame does not reach during combustion, giving high HC emissions. Soot is produced with very rich mix at high temperature, and NOx is a product of lean mix at very high temperature. To reduce pollutants at source, we must manage both gas composition and temperature during combustion. We will mainly discuss technologies for soot and NOx reduction at source because today emission is a bigger problem for diesel engines than it is for gasoline engines. And as we have already seen, soot and NOx are the main emissions for diesel. The first example we'll take is exhaust gas recirculation or EGR. This technology is mainly used to reduce NOx at the source. As the name suggests, a part of the exhaust gases are reintroduced at the entrance of the engine. Due to CO2 produced during the combustion, there is an excess of CO2 in the exhaust gases. Therefore, using EGR, the amount of CO2 in the mixture inside the engine increases. As a result, the relative amount of oxygen goes down. Because CO2 is not involved in the combustion, EGR actually increases the fraction of unreactive gases in the mixture. These unreactive gases act as the heat sink during combustion, and as a result, combustion temperature goes down. Although the desired effect was as shown by the arrow on this graph, the actual effect of EGR is like this. As a result, the combustion enters the soot formation zone, resulting in an increase of soot and in turn increased smoke. This is the downside of EGR. EGR is a standard for modern diesel engines today and is increasingly becoming popular in modern gasoline engines with direct injection. As a second example of pollutant reduction technologies, let's explore Common Rail Direct Injection System, also known as CRDI. It is mainly for soot reduction. The idea is to inject the fuel at very high pressure into the engine. The pressure can go as high as 2000 bar for diesel engines. Fuel injected with this high pressure atomizes rapidly, giving very small droplets, which mixes quickly with the air around the jet. It can be seen in this blue picture of the simulation of high pressure jet injected in a gas. In the middle, you can see a typical common rail system with injectors shown in green and a common rail attached to them at the back. In the case of diesel engines, as the jet is at very high pressure, it could reach the walls, causing droplet deposits at the wall. Now to avoid this, a swirl motion is introduced inside the engine. Use of swirl and high pressure injection ensures better mixing, which as a consequence avoids pockets of rich zones. As a consequence, local richness decreases as shown by the arrow here, and this reduces soot. However, in reality, instead of following this arrow, we follow this arrow here towards the zone of NOx formation. Therefore, as one of the drawbacks of CRDI system, NOx rises. The last technology we will see is the alternative fuels. Fuels like ethanol and natural gas are less carbon intense in comparison to gasoline or diesel. They have higher number of hydrogen atoms per carbon atom. Therefore, during combustion, more H2O is produced than CO2. Consequently, they tend to produce lower CO2 when compared with the combustion of gasoline or diesel. Also, these gases have smaller and simple molecules, giving cleaner combustion. It results in less soot formation. Due to these advantages, these fuels are mixed with more conventional fuels and are often used in some engine technologies. These mixed fuels are called dual fuels. Prominent example being ethanol with gasoline, natural gas with gasoline, and natural gas with diesel. We will end our discussion on pollutant reduction at the source here, and in the next video, we will explore current after-treatment technologies for pollutant reduction. So keep watching. Thank you.